Okay, greetings students. So we'll be starting the lecture. So first we'll be starting with the equivalent circuit of your transformer. Okay, so in the previous lecture, we have seen about the phasor diagram of the while at your no load. So with the resistive load, with the inductive load as well as capacitive load, we have seen. And in today's lecture, we will be dealing with your equivalent circuit of your transformer. Okay, so before getting into the equivalent circuit of the transformer, you have to know why we have to go for your equivalent circuit. What is the purpose of your equivalent circuit, and what do you mean by this equivalent circuit? Okay, so for example, the things whatever we are seeing in our nature, you can completely convert that into mathematical expression. Mathematical expression. Okay. So how I am saying this means how you can model this mathematically means, for example, you can take a leaf. You can take a leaf, and in that leaf, for example, that leaf is present during the rain, rainy condition. So the raindrops is falling over this leaf. So when the raindrops falls over this leaf, okay, so the leaf normally gets displaced. Okay, it gets displaced by up to this position. Okay, so what happens is while this vibration occurs, there will be a sinusoidal waveform. Okay, due to the sinusoidal waveform only, you will be hearing sound. Okay, so this is an example for a mathematical model that is taking place in your nature. Okay, the sound vibration which is coming from a normal natural situation or a natural case will be, you can easily model in terms of your mathematics. Okay, so this sinusoidal waveform you can easily model in terms of your mathematical model. Okay, so similar to that, in your transformer can also be mathematically modeled. Okay, so for that only you need this equivalent circuit. So we have seen the transformer as like this structure we have seen. So this structure can be completely mathematically modeled into a circuit like this. So this is the equivalent circuit of your transformer. So here you can see the circuit is a no load. So this is your no load equivalent circuit. Here you can clearly see that there is only your primary, but there is no secondary. Why means the secondary exists only when there is load. Okay, so when load exists, your secondary side will exist. Okay, secondary side will exist. Otherwise your secondary side will, you can omit it. Okay, so now we are taking with respect to your no load condition. So in your no load condition, there won't be secondary side, so there will be only your primary side. So the I have already said about this current. Okay, so this is your current flowing at your primary when there is no load, so it is represented by I naught. So apart from this I naught, there will be two more components. Okay, at your primary, first starting with your magnetizing component. So this magnetizing component is the current which is flowing through your inductor. Okay, at the same time, the active component IC, this is your active component. This is flowing through your resistor. Okay, so if you are converting this transformer into a circuit means you will be getting like this. Okay, but this is a no load equivalent. So here you have to know that this r naught, value is nothing but the voltage drop applied is V1 divided by the current flowing through it, that is your IC. Okay, at the same time your inductive component x naught. Okay, your x naught is this, the same voltage drop, because these are in parallel. This R naught is in parallel to this X naught, which is in parallel to the voltage, applied voltage V1. Okay. So it will be your V1 divided by the magnetizing component Im. Okay. I hope now we got the idea for the equivalent circuit, why we are going for the equivalent circuit, and the no load equivalent circuit we have seen. Next is that equivalent circuit parameter referred to your primary and secondary sides. Okay, so we have to particularly keep one point as a reference, keep one thing as a reference, one parameter or one side as a reference, and you have to compare with that. Why I am saying this? The previous case here we have seen that the leaf was in the first position before your uh, before the raindrop falling over it. Okay, so after the raindrop falling over it, due to the weight of the raindrop, the leaf moved to your second position. Okay, so here you'll be having a reference point. So this first one is your reference point. Okay, so based upon your reference point only, you can find this displacement, and as per this displacement, you can calculate your sine wave. Okay, so similar to that, similar to this example, so here also you will be having one side, you'll be taking one side as a reference. Okay, you have to take the one side as your reference. Okay, so after that you will be comparing that side with your other side. Okay, for example, if you're taking primary as a reference, means you'll be comparing your primary with to your secondary. Okay, so here they have given this is a diagram. Okay, at your, this is your primary side. Okay, this is your primary side, and this is your secondary side. Okay, this is your primary side and this is your secondary side. So up to this, this is up to this, you'll be having your no load equivalent. So now we are connecting your load ZL. Okay, now if you are connecting your load ZL, so what happens? Okay, so this R2 and X2 will be coming over here. Okay, and the voltage drop will be across this load will be V2, and the induced EMF will be E2, and the induced EMF for the primary will be E1. Okay, here it will be E1 and here it will be E2. Now you have to see what is this I2 dash. Okay, so I'll be saying. So now we are converting with respect to your primary. Okay, so at that time the effect of circuit parameters shouldn't be changed while transferring the parameters from one side to another side. Of course, it should not change, right? So for example, if you are secondary, you're having a current flow of secondly you're having a current flow of 5 amps. Okay, here you can take it as a 5 amps I2. Okay, but if you're transferring this to your primary side, or if you're comparing with the reference of the primary side, means it also should be of your 5 amps. This 5 amps should not be changing. Okay, it should not be changing. Okay, it should not be changing. So that's what they have said in this point. Okay, it can be proved that resistance of R2, okay, resistance of R2 in your secondary is equivalent to the R2 by K dash square will be denoted as R2 dash. So here what they're saying is that in order to bring your secondary to primary, you can make use of your transformer turns ratio K. Okay, so we have seen about K already. So based upon this K, you can do it. So if you are doing with respect to K, means your R2 dash will be equal to R2 by K square. Okay, so this is the thing. If you are bringing your load side or the secondary side resistance towards with reference to your primary side. Okay, so here how they are giving out, they are saying how they are deriving the relation they have saying. Okay, the equivalence secondary resistance with respect to your primary, which would have caused the same loss. Okay. So as I said in the first case, the parameter current should not be varying when you are converting from your secondary to primary. So here you can take the losses to be the same. Okay, the losses are same means so it comes like this, because here this corresponds to a copper loss, okay, or I square loss. So this loss, about this loss, what is that means? If a current is flowing in a wire from A to B, okay, so if this current flowing is around 10 amps, okay, but excess amount of current up to 22 amps is flowing in this A to B due to some fault. At that time, what happened is that this wire gets heated up. It gets heated up. Okay, so there will be a lot of losses due to the heat. So this is called as your I square R loss. Okay, so there will be I square R loss in this wire from A to B. Okay, so that's what it's also called as a copper loss. So now the equivalent resistance of transformer when referred to your primary. So now we have got with respect to your R2 dash. So your R2 dash is nothing but your R2 by K square. Okay. So now this R01 is here referred to the primary. Okay. So R01 is equal to R1 plus R2 dash. So that is R01 is coming around here. Okay. So now it is in series. This R2 dash is replaced by this value what we have found in the previous slide. Okay, the same thing is applicable for your inductance. Okay, how we found your resistance, the same exact thing is applicable for your resistance also, sorry, inductance also. Okay, now we are transferring your secondary parameters to primary side. Okay, so here at this side in this diagram, if you are seeing means there won't be any secondary side. There won't be any secondary side. Okay, so y means we have completely converted your secondary side into your primary side. Okay, so now this is a equivalent circuit with refer to your only primary. Okay, so up to this the your no load equivalent circuit, so it will be the same. So after this only you have to draw with respect to your R2 dash and X2 dash. So these are nothing but the equivalent circuit parameters which is referred to your primary, what we have found out in the previous slides. Okay. Similarly for your load also. So now after transferring parameters to the with refer to the secondary, okay, this is what your circuit with reference to your primary. Okay, reference to your primary. And in the next slide, what we will be seeing is about with the reference to the secondary. So here at this side, there won't be any primary. Okay, primary is absent. Primary is absent, but here this is entirely filled with respect to your secondary. Okay, so this is the two cases for your equivalent circuit. Okay, so here you can see the with refer to the primary, what you have seen was R2 equal to sorry, R2 dash equal to R2 by K square, right? But over here, if you're converting from your primary to your secondary means, okay, this is a total equivalent circuit. So if you're converting from your primary to secondary means, okay, if you're converting from your primary to secondary means, so what happens is that your R1 dash will be equal to K square into R1. Okay, you can see the difference, right? So this is for a case 1 and this is for a case 2. Okay. Similarly, we have to find the parameters. and this is what your equivalent circuit looks like. So again, they are saying with respect to your primary. Okay. So this is what your approximate equivalent circuit at no load. Okay, this is for the no load approximate equivalent circuit. Okay, so these are the things with respect to your equivalent circuit. With this, this lecture is over, and we'll be moving on to the next.